Hello, grade 6. Welcome to another math lesson. So we're still finishing up Unit 1, Patterns and Equations, right? We're focusing more on the equation side of this. We're going to be discussing what's called commutative properties today, right? And how that kind of relates to what's equality. Here's another link to a video if this to help explain kind of everything we're going to be talking about. This little Star Wars star math expression. Right now, some of us are able to look at that and figure out an answer, and if you can, what you're trying to do is you're trying to find what does the TIE Fighter equal, what does the Millennium Falcon equal, what does the X-Wing equal, and what does the Destroyers equal, because they all have different numerical values. If you can't get it now, hopefully by the end of, I guess it will be Tuesday's class, hopefully you will have an idea of how to at least approach the question. So we're just going to quickly review lesson 6. Again, there's a video attached if you need to review it or if you need more time on that. What we did is we just kind of finished drawing graphs. I've explained this to some people, but what you need to know more is identifying graphs. Now we drew them, but the big thing is for the quiz that's going to be coming up, we're seeing the graphs and saying, hey, I understand what this is saying, I know what the pattern is. And that's kind of what we talked about is patterns, right? We have different ways to represent patterns. Now we can represent it as an image or as a table, right? The first figure is going to be your first coordinate, right? That means figure 1 in the one column of a graph. So if we have a graph like this, and we have 1, 2, 3, in this first area here, right here, where there's the 1, that's going to be your first coordinate, right? Because it's figure 1. The second coordinate is going to be the number of tiles. So we're going to count the tiles. That's going to be 3. So if there's, again, on this graph, what we have here, we have 1, 2, 3. So you'll have 1 because it's the first figure, and you have 3 because that's how many tiles there are. Number 2, right, would be at the 2 section, and it has, count them out, it has 5 tiles. So it'd go 2 and 5. Okay, and the same thing's happening here, 1 and 3, 2 and 5, and they're writing out them as a pair of ordered pairs. Okay, and that's kind of what we covered. So with that, we discussed how you can draw it with a graph. And when you start drawing these things, and this is what they did, is they did it for us, right? As they draw them out, you can actually put them on a graph, and you can show how they are related, right? And so what happens is they talk about, and this is kind of how we want to start putting it into words, where you want to get from one point to the next, you have to move one space to the right, right here, 1 to the right, and then you have to move 2 spaces up. We said you have to be careful here because make sure that these are scaled 1 to 1. If not, then one of these squares will not equal to two spaces, or sorry, one of these squares won't equal 1 spaces. It would equal to whatever is in the scale. But as of right now, we have +1 to the right, and we have +2. That's the relationship. Now, based on that, we should be able to realistically predict where. So the last place we ended up on this one, let's just give a little highlighter, is the 5th, right? If we had enough space upward, we could predict all the way up to the 10th. And the way we do that is we take this last dot and we move 1 to the right and we go up 2. And that's going to be the home for our next dot, right? And we continue that pattern and we can predict what's coming up. You're going to have some questions like that on our review today. And this is just kind of the last thing. We graph the relationship, we show it, and this is really the phrase that we came to know and we need to understand. So as the input increases by 1, the output increases by 3. Or as we move right 1, right, we're going to move up 3. Because remember, the output equals up. Up. That's a bad up. But you got the point. Today we're going to talk about commutative property and equality. So the first thing is understanding equality. This here is an equation, right? This represents an equation. So much like on a scale, if something is more balanced, if there's more of something, it will be unbalanced, all right? And so what happens is, what a scale is, or an equation is you have an expression on one side, and you have an expression on the other side. And they are only ever equal, right, if they have the same value. So with this one we have 3 and we have 3, right? 3 equals 3 and we know that's true. The moment though that we start adding on to these, so the moment we add on, let's say, what is here? Alright, this is no longer equal and this side is going to be heavier. And this is also true when we try to, and what we're leading to is solving about variables. Alright, we want this scale to be balanced. We want the 3 to equal the 3. And so this is with pictorially, but we also have to do it with numbers. Alright, and so what we can have is this is another example of an expression. 3 plus 1. Another expression is 7 minus 3. They both equal to 4. So even though it's not in images, the expression still equals the expression. Right? And that's really important. So what we're going to do here is I want you to pause the video, take some time. I want you to look at these expressions here. Alright? And I want to see if you can match which expressions do they line up with. So what other expression will 4.5 equal on here? Alright, so I want you to pause the video because I'm going to solve it in 2 minutes. Not even. Alright, so 4.5. So what I'm going to do is I'm going to look for something that's going to equal to 9. Right, as I scroll down, I find 5 and 4. Alright, 3 times 5 is going to be 15. So what other thing is also going to equal to 15? 5 times 3. Alright, 17 minus 10, that's going to equal to 7. So what else here is going to equal to 7? We're just going to go through, That's wrong. What's wrong, Mr. Callum? Oh, I erased those. Rats. I can't actually find it. It might be on another side. We'll move on from that one for now. 21 minus, so this is going to be the thing that we're going to talk about here. Is we're actually going to get into quite the pickle here. So we want something to equal to 11 right here, right? So this is kind of interesting because these are equal and they have different operations. These are equal, let's see, right? But you notice that they're just the same numbers flipped, and those are what we're going to focus on. That's called the commutative property. Okay, so let's keep going through. I still can't find another 7. I know you're probably staring at it right now. This is what happens when all the pressure's on you. Oh, I found it, because it's right here. Alright, 18 divided by 6, that's going to be 3. Let's find another one that's also 3. Oh, found it right here. 27 divided by 9. 2 times 4 is the same as 4 times 2, which means these two are also paired together. Alright, so what we're just showing though is that with different operations, different expressions, that's really the word we're focusing on, expressions. Right, different expressions can have the same weight and they can balance and equal each other out, right? Because these will be equal. So expressions can have different, look different, but they have the same weight, they have the same value. So if you see these scales below, right, each of these scales, they are balanced. For each of the scales, the expression on one pan is equal to the expression on the other. It doesn't matter if they have different operations. We use the sign to equal signs to show that they are equals. This is, I know this seems very basic, but it's also very true. We take for granted that 36 divided by 6 equals 6. What we're saying is that they have the same numerical value. So it's the same way of saying this is equal to this. Even though they look different, they both represent 6. Alright? So we can represent that in a sentence as 36 divided by 6 equals 15 divided by 9. Alright? These next two examples are where we get into commutative property. 12 plus 5 will equal to 5 plus 12. 3 times 7 will equal to 7 times 3. Order does not matter. All right, so this is called the commutative law of addition. We're going to start with this one first. This is a property that states numbers can be added in any order and that won't affect the sum. All right, so it doesn't matter. So what that essentially that means is 24 plus 13 is the same thing as 13 plus 24. And we're going to kind of show you why using cookies, and we're going to do it a little bit more basically. All right, so 3 plus 2. Let's say I have 3 cookies. These are things that I already have, and I add 2 to them. We have a total of 5, right? What we're saying is this is the same thing as if I start off with 2 cookies and I add 3 to them. All right? We still have 5. So it doesn't matter the order of this. It doesn't matter if I'm adding 2 cookies and I started with 3, or if I started with 2 cookies and I added, sorry, I confused myself. It doesn't matter if I started with 3 cookies and I got 2 more from, let's say, a friend, or I brought 2 cookies for lunch and the friend gave me 3. It doesn't matter which order it is, the addition, I still end up with 5 cookies. All right? We can do this, we can show with this with variables through the expression here. All right? Any pair of numbers, a plus b will be the same always as b plus a. We can change that order when we're doing with addition. We can also look at the associative law. Sorry, let's explain the commutative law a little bit better. All right? What I like to think of commutative, the root word is to commute. Commute means going back and forth. If I have a house, right, and I walk to school every day, this is the school, and it's 5 miles or kilometers. Let's do kilometers. Right? If it's 5 kilometers to school, it's always going to be 5 kilometers back. Right? That's the same thing. If it's 5 kilometers to school, it's going to be the 5 kilometers back. All right, so it doesn't matter if I'm walking there or walking back. It doesn't, as long as I'm taking the same path, it will be the same. And so what that means is, if I'm adding the same things, it's going to equal the same way. All right. I know it seems kind of obvious, or maybe it's so obvious it's confusing. It's very clearly different than subtraction, and I'll show you why that is. All right, let's say I have 3 cookies and you take 2 away. Right, we all know that means how many cookies I have left. I have 1. Okay, but according to this, right, I should be able to do 2 minus 3, and it should also equal to 1. But we know that's not the case. If I start with 2 cookies and I can't take 3 away. So this law doesn't apply to subtraction. The law only applies to addition and multiplication, because we can't switch these numbers like we can here. Another example is associative law. All right, and so what that is that's when we start having these brackets here. I'm just going to redraw them. All right, so if we have in brackets 1 plus 2 plus 3, we're saying that will also equal 1 plus 2 plus 3. All right, so remember, according to BEDMAS, right, we have to do our brackets first. So this is going to equal to 3 plus 3. This is going to equal to 1 plus 5. Okay, these are both going to equal to 6. So it doesn't matter where we change these brackets for addition, because these are the same numbers. It doesn't matter where we change these brackets, it's still going to equal the same thing. It's very similar with multiplication. Right? So I'm not going to have to read this out, but in multiplication too, we can change the order without affecting the product. Right? So this was previously 7 times 11, and now it's 11 times 7, and it's going to equal the same thing. We can represent that this way in variables. And much like in addition, when we have brackets, right? When we have brackets and we do them first, if we change the brackets, we will still get the same thing. 1 times 2 is 2, times by 3. 1 times 2 times 3 is 6. So once again, they're both going to equal to 6. Okay, so the brackets doesn't matter. In both associative, and when I say associative for our context, just think about brackets. Right? Whether there's brackets or whether it's just 7 times 11, the order does not matter. Now let's look at an image for multiplication. All right, so this is going to be what we're working with. 3 times 4. All right, 3 times 4 is going to equal to 4 times 3. What this means is we have 3 groups of 4 things, or 4 groups of 3 things. And I'm going to show you how it's going to be the same. Okay, so if I have 3 groups, I'm going to group these acorns into 3 groups. This is 1 group, 2, and 3. Right? So I have 3 groups of 4 acorns. Right? 4 things would be the acorns. This is the exact same as having 4 groups of 3. So it doesn't matter what order I change. Right? I have 4 groups of 3. Right? It's really just the shape. I can change how this looks. So again, if I have 3 groups, let's draw it out. 1, 2, 3. Of 4, 1, 2, 3, 4. I have 12, right? Whereas if I have 4 groups, 1, 2, 3, of 3, I still have 12. All right? These numbers are the same. It doesn't matter the order of which I multiply them. Hope that helps. If not, if you're more of a number lines person, that's okay too. Let's say that this is going to be 3 jumps with a size of 4. So this is going to be my size. Or 4 jumps, let's use another color. 4 jumps with a size of 3. Okay? So 3 jumps with so you start at 0. You always start at 0. You're going to do 3 jumps that are 4 jumps long. So you got 1 jump to 4. Right, that's 1. You got 2. You got 3. Right? So you got 3 jumps. They're the size of 4, and we got to 12. All right, let's see if that also works with this other version. All right, we're going to have 4 jumps, size of 3. 1, 2, 3, 4. Right? So once again, we're just proving with visuals that 4 times 3 and 3 times 4 are equal. Now that might seem, again, super obvious to us, right? But what it's doing is it's introducing what actually equality is. And it does matter, because once again, let's get into division now. Why is this work for multiplication, but it doesn't work for division? Okay? So if I have 12 divided by 4. Okay, so I have 12 acorns here, and I'm going to break them off into 4 groups. That's really what it is, right? 4 groups. 1, 2, 3, 4. Okay, that works. I know I'm going to have 3 acorns in each group. But what I can't do is I can't switch these. I can't switch these, and it doesn't make any mathematical sense. Because 4 divided by 12. So let's say, for a moment, all I have is 4 acorns. Okay, so I'm just going to cancel these out. Ignore this. I have 4 acorns, and I want you to break them into groups of 12. Well, you'd have to chop these up, right? So it's not going to equal to 3, which we had before. So while it works for multiplication, it doesn't work for division, because I can't draw this. I can't divide this into 4. Well, I can, so I can't divide it into 12, but I'd have to split it up, chop it up. Okay? So I hope that kind of makes sense why we're taking so much time on this. For it could be a short video. Again, you always have the ability to skip ahead whenever you want. So yeah, associative law of multiplication. So now we talked about cumulative law, associative law. Essentially what that means is look at these two. Which one do you think is easier to solve? Which one's faster? And this is the whole idea of associative law, is you can move these any way you want. Alright? So maybe you're looking at 4 times 5 times 2, and you're like, I know that one right away. Maybe you're looking at 5 times 2 times 4, and you're like, I know that right away. Either way, right? What we're doing is we're inserting brackets at certain points. Okay, so we're inserting brackets around 4 times 5 because we're going to do that first. This is what we do in our head. This is grade 3 stuff. Alright, so we know that's 20. We times the remainder by 2, we get 40. Same thing here. Different order, but we put the brackets around something differently, but we get the same answer. This is really, so the real reason why this helps is it helps with reordering things. So if I show you this, this addition question, right? What I can do, because I don't know about you, I looked at that right away, and it's a little bit even. Odd numbers always kind of confuse me. But what you can do is this number can go right here. So that becomes 9d1 plus 9 plus 37. Right? 91 plus 9, well, I know 1 plus 9 is 10, plus 90, that's going to be 100, plus 37 equals 137. That's our answer. Okay? So again, it just helps us through rewriting these and putting it easy in order. Same thing, I don't know 4 times 17, but because of the associative law, I can move this here. 4 times 25, well, I know that. It's got to be 100. Right? Times by 17, sorry. That's going to be 100 times by 17 equals 170. What you're going to see, what we're going to do is we're just going to work on this, because what you're going to see next class is you're going to see questions like this and say, are these equal? All right? And you're going to have to figure that out. Here's a review. Basically, cumulative law. We have addition. You can add in any order. You can switch, like especially when it's 1 and 1, you can switch those around. Same with multiplication. Here we have a visual, right, of proving how 6 plus 3 also equals 3 plus 6. This will be a question you have on your worksheet. Notice how these visuals, how they draw it out. They show how 2 times 4, 4 groups of 2, right, 4 groups of 2 equals to 2 groups of 4. Okay, that's very important. So this is a really long video for something that didn't need to be that long. If you stuck around, high fives to you. If you need more help though, there are a ton of videos on Khan Academy that help explain it. It's going to be a lot shorter. Those are like 4 minutes. And here's some extra practice problems. Alright, please go do the homework. And let me know if you have any other questions. Alright, we're going to end this video now.